In our previous example, we were interested in internal loads at 3 discrete locations. Here we have 2 structural members, one that's straight and one that's semicircular. We're neglecting the weight of the members, and for each member we want the internal forces acting on cross-section C. Note that in this case, the position of C is not well defined. For the straight member, it's at some distance x from roller A, and for the semicircular member, it's at some position defined by angle theta from roller A. For these cases, we'll be able to construct expressions for internal forces as a function of position. We could begin with free body diagrams for both of these members. We would have a single roller support at A, and because this is a pin, we would have forces Bx and By. These would be the same for both of these cases. And we can see right away that what we're going to end up with here are 2 force members. Sum of the moments about B is going to produce A equals 0. Sum of the forces in Y is going to produce By equals 0, and then we're going to be left with Bx equals minus P. We'll begin then with free body diagrams based on these enveloping surfaces for the 2 members. For the straight member, we have our load at P. Our roller support provides A equals 0, and then we have axial load NC, shear force VC, and bending moment MC. And these are at some distance x from roller support A that has not been specified. Our equilibrium equations, based on a traditional xy coordinate system, will simply give us NC plus P equals 0, or NC is minus P. In the y direction, we'll have VC equals 0, and we could take moments about a couple different places, but I'll choose to take moments about A, in which case we have the bending moment at C plus the contribution from the shear force through a moment arm X equals 0. But we've determined that VC equals 0, so the bending moment at C is also 0. So what this tells us for the straight member is that the internal loads consist entirely of an axial force NC equal to minus P anywhere between A and B. For the semicircular member, our free body diagram will look like this, and we'll make a note here. We're going to use a different coordinate system that will be much easier in this case. Our angle theta is here, and we'll be better off using a coordinate system that's an r theta system. We'll have a normal force, shear force, and a bending moment. It will be important for us to break P into components in the r theta direction. We'll note that theta is here, and so we have a component P in the theta direction that will be equal to p sine theta and a component of p in the radial direction that will be p cosine theta, but in the minus radial direction. We might also note that this vertical distance is r sine theta. Now our equilibrium equations in the radial direction, we have Vc minus p cosine theta is 0. In the circumferential direction, we have Nc plus p sine theta is 0. And taking moments about c, we have the bending moment at c plus the contribution from p, which is now just p times the moment arm, r sine theta, and is positive, is 0. So our result is Vc is p cosine theta, Nc is minus p sine theta, and Mc is minus pr sine theta. Now, the sketch that's made above is based on theta being an acute angle. We might ask if anything changes if theta is an obtuse angle. The short answer is that it doesn't, but we can take a few minutes to sketch out how the problem will change when theta is an obtuse angle and just make some comments then on what's the same and what's different. Here we have a sketch of what would be different if theta were an obtuse angle. We're still going to use our polar coordinate system with r and theta, and we still have to resolve p into components in the radial and circumferential directions. On the basis of this sketch, and using the fact that cosine of pi minus theta is minus cosine theta, and sine of pi minus theta is the same as sine theta, we could show we get exactly the same expressions considering theta to be an obtuse angle as an acute angle. As to which one of these two force members makes a better truss member, the answer is the straight one. The internal forces in the straight member consist entirely of the normal force or the axial force along the member. There is no shear and there's no bending moment. This means that the truss member is going to react loads along its length as efficiently as possible with minimum deformation. The presence of the shear and the bending moment in the arched member, in the semicircular member, means that it's going to be able to react the load but only with significant deformation. So, from a standpoint of reacting load, the straight truss member is definitely better. Finally, we consider a three-dimensional internal force problem. Here we have a body which is built in to a support at O, and there are a couple different locations where we might look for internal forces. Specifically in this case, we're asked to determine the internal forces acting on the cross-section C. We could begin this problem by finding the reactions at O, but we really don't need to do that. Instead, we can simply base our free body diagram on this cut that envelops this outer part of this surface. So our free body diagram now for CBA will be based on this. We'll just make a note that our XYZ coordinate system looks like this. We have a force of 200 pounds in the minus Y direction out here at A. We have a force of 50 pounds in the Z direction at B, and we'll have a full complement of internal forces at C. We have a normal force in the y direction and shear forces in X and Z. We also have moments in all three directions. Mx, My, and Mz. Our equilibrium equations will be these. In the x direction, we have simply Vx is equal to 0. In the y direction, we have Ny minus 200 pounds is 0, or Ny is equal to 200 pounds. And in the z direction, we have Vz plus 50 pounds is 0, or Vz is equal to minus 50 pounds. For taking moments, I'm going to take moments about C. And we could do this as a scalar approach, but in three-dimensional problems, I always like to use a vector approach. So I'm going to take some of the moments about C equals 0. And we have at C, we have Mx and I plus My and J plus Mz and K. Looking at the 50-pound force, our position vector from D to B is 12 inches in the minus J direction. We're crossing that into 50 pounds in the K direction. And then we have our position vector from D to A is 18I minus 12J inches crossed into 200 pounds in the minus J direction. Now we just might note here, J crossed into K is I. This is going to end up being minus 600 inch-pounds in the I direction. Down here, J crossed into J will yield 0. I crossed into J will yield K. And we have minus 3,600 inch-pounds in the K direction. So our result is Vx is equal to 0 pounds. Ny is 200 pounds. Vz is minus 50 pounds. And if we collect the terms in I, J, and K together here in our moment equation, we see that in I we have Mx minus 600 inch-pounds is 0, or Mx is 600 inch-pounds. We have My, but nothing in J, so My is 0 inch-pounds. And collecting components in K, we have Mz minus 3,600 is 0, so Mz is 3,600 inch-pounds.